Hello, and welcome to the electrical system lesson in the PMDG 737 Next Generation Groundwork from Angle of Attack. This lesson will cover the following topics: electric power description and types, 737NG electrical system overview, AC electric buses, DC electric buses, DC power sources, AC power generation, standby electric power system, electric system control panels and indicators, and a lesson summary. In general, electric systems may have interfaces and schematics that are very hard to understand at first. For this reason, we're going to discuss the 737NG electric system in a basic way, so that essential elements can be easily understood and non-essentials can be left out. When in doubt, always refer to the PMDG 737NG Flight Crew Operations Manual or simply leave a message in the comments section of this video. Electricity is the presence of an electric charge that flows within a circuit when excited in order to produce energy. Subatomic particles, known as electrons, are the ones that flow inside a circuit. When this occurs, a little magnetic interaction also takes place. This magnetic interaction is known as a charge. For example, electrons are charged negatively. However, a stable atom has an equivalent amount of protons that are charged positively within the nucleus of the atom. When an atom is excited, it may either lose or gain electrons in an attempt to restabilize itself, thus producing a positive or a negative charge. When charges move around the circuit, they are known as currents. There are two types of electric currents: direct current, DC, where electricity flows in one direction; alternating current, or AC, where electricity flows in two alternating directions. Direct current causes electron flow in one direction by a magnetic field near an electricity conductor. However, it can carry only a fixed amount of energy and usually loses it as and when the current travels a distance. In contrast, alternating current does not lose energy and it can carry a significantly higher amount of power. A variable magnetic force is used to achieve alternating current. DC output energy per charge, or voltage, is constant, whereas AC voltage may be transformed into different values. AC current's output power versus voltage are measured in a unit called volt-ampere, generally expressed as thousands or kVA. Another important concept associated to AC current is the frequency at which the current alternates direction. Frequency is measured in hertz. For example, a 60 hertz frequency is equal to 60 current direction changes per second. Let's now talk a bit about the 737NG electrical system architecture. The electrical power system generates, supplies, and controls electricity for various components in the 737NG that rely on it. Most elements and components aboard the aircraft rely on electricity, either directly or indirectly, for their operation. A few of these are flight deck avionics and display units, landing gear motor, trailing edge and leading edge devices retraction extension actuators, aircraft lighting, and other elements. For this reason, overall redundancy and safety built into the electrical system is considerably high, as many essential components depend on it. We'll discuss this idea progressively as we move through the lesson. Both AC and DC currents are generated and supplied for the respective aircraft systems via wires and cables that conduct electricity. These wires are insulated to protect from contact between two different sets of cables. It's extremely important to keep cables metallically isolated from each other with insulation. Failure to do so may cause short circuits or other weird effects. If you don't believe us, ask Ms. Susanna Darcy, a veteran Boeing test pilot who was once testing a 737NG. Whenever she would turn the aircraft electric power on, she and her test team would notice that all the flushes in the lavatories would activate. This was due to some form of interference between electric cables. The entire electric system has both manual and automatic controls, as well as standby AC and DC systems to provide an emergency source of power. We must also be familiar with the concept of an electric bus. Buses are essentially electric platforms from which electricity is both supplied to and drawn from by the respective aircraft systems. Each electric current type has a respective set of buses for both essential and non-essential items. The whole purpose of buses is to allow essential items to still remain powered if there was an electric power shortage or emergency. During an electrical emergency, it is far more important to have an active, functional communication radio as opposed to having functional strobe lights. For this purpose, both items draw current from different electrical buses. The 737NG uses both AC power from engine-driven generators and DC power that's stored in a main battery and an auxiliary battery. Before having a deeper look at where the 737NG gets its electric power from, let's talk about the available electric buses on it. The AC electric system has two primary buses that take all the generated AC power and divide them amongst smaller AC buses. AC current is supplied as 115-200 volt 400 Hz power. The two primary AC buses are known as AC transfer buses 1 and 2. AC transfer bus 1 subdivides into the following buses: AC main bus 1, AC ground service bus 1, galley bus C and D, AC standby bus. The AC transfer bus 1 also supplies electrical energy to the DC bus 1 through a component known as a transformer rectifier. We'll discuss AC to DC energy transformation and DC buses later in this lesson. Similarly, AC transfer bus 2 also subdivides into the following buses: AC main bus 2, AC ground service bus 2, galley bus A and B. AC transfer bus 2 also supplies energy to the DC bus 2 with another transformer rectifier. Notice that the AC standby bus is partly AC powered only by AC transfer bus 1, but it also has a part which is powered by AC current derived from the DC electric system. DC to AC conversion is achieved with an inverter and will also be discussed later on. Moving on, the DC current system supplies and controls 28-volt power. It's comprised of the following items: DC bus 1, DC bus 2, battery bus, hot battery bus. The DC system has the following power sources: 28-volt battery, battery charger, transformer rectifier units, or TRUs. We mentioned the TRUs before, so let's explain them now. The 737NG has 3 of these components, which essentially transform and rectify the 115-volt AC power to unregulated 28-volt DC power for the DC buses. The 3 transformer rectifiers are connected in parallel, which means if one of them fails, the other 2 may give backup. The TRUs are connected according to the following logic. TRU1 gets power from the AC transfer bus 1 and connects directly to the DC bus 1. TRU2 gets power from the AC transfer bus 2 and connects directly to the DC bus 2. TRU3 gets power from the AC transfer bus 2 and provides a power source for the battery bus. If power from the AC transfer bus 2 is lost, AC transfer bus 1 may supply backup power to TRU3 through a relay. The DC system has 2 batteries, one main battery and one auxiliary battery. Both batteries are 48 ampere and 24-volt DC power sources. In very simple terms, the battery's connection logic is the following. The main battery normally only supplies power for APU starting, but is a standby power source when all other power sources are inoperative, such as during a complete loss of AC power if both engines are shut down in flight. We all know that the chances of this occurring are minimal. However, the redundancy must still be built in to make the systems more reliable and dependable. Both batteries are always kept at maximum charge by a main and auxiliary battery charger, powered by the AC power system. In case the batteries were ever to drain on ground, it takes nearly 3 hours to charge the batteries from zero charge to an operational level.